Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So we are looking at this problem. So the problem that we want to solve is division in uniform NC1, and as I said, so this is a result due to Cook, Beam and Hoover. Okay. So what we have seen so far is, so last time we saw that suppose if we want to compute iterated product, okay. So we have already seen that we can reduce division to the problem of computing iterated product, and in fact we can reduce division to the problem of powering, and powering is just a special case of iterated product. So our target is to show that we can compute iterated product in uniform NC1. So what have we seen so far? We have seen that we can compute iterated product modulo a prime power, a small prime power in uniform NC1. That is something that we have seen, and another result that we saw last time is that this Chinese remaindering theorem. So we saw that Chinese remaindering theorem can be reduced to the problem of computing iterated product. Okay. So that is what we have seen so far. So essentially what it boils down to is how do we solve iterated product. Okay. So that is what we are going to focus on today, and we will complete the proof of this theorem. So before getting into the result that we will be proving, let me start with a definition. So we will define something called a good modulus sequence. Okay. So a good modulus sequence is a sequence M1, M2, so on, such that Mn has two properties. Mn is at least 2 raised to the power n and at most 2 to the power n to the power d for some d greater than or equal to 1, and the second property is that for all prime powers such that p raised to the power l divides Mn and p raised to the power l plus 1 does not divide Mn, p raised to the power l is at most r of n for some polynomial Rn. Okay. So basically a sequence is a good modulus sequence if there exist two things. One is there exists a constant d greater than 1, another is there is some polynomial Rn such that the nth value of the sequence mn is between 2 to the power n and 2 to the power n to the power d, and every prime power that divides mn is small in some sense, okay, it is bounded by the polynomial r of n, okay, so it is not too large. So one thing, if you just d is a constant, t does not depend on n, it can be any constant, okay. So yeah. Let me write it over here, some constant d greater than or equal to 1, okay. Now I mean if you just look at this, so d equal to 1 actually will not work, because if I set d equal to 1, it means that m of n is exactly equal to 2 to the power n, and 2 to the power n, the only factors of 2 to the power n is 2, the only prime factor, and the highest prime factor is 2 to the power n itself, and 2 to the power n is of course bigger than any polynomial. So d equal to 1 does not work, so I mean without any loss of generality I can remove this, but yeah, I mean d equal to 2, 3, I mean they might work, in fact we will see. So let me give some examples. So some examples. So one example is mn is the product of first n primes, okay. So if you look at the first n primes, you can show that it lies between, it is greater than 2 to the power n and it is less than actually 2 to the power n square, okay. And of course the product of the first n primes, the only prime divisors are the prime itself, and the nth prime by the prime number theorem is at most n log n. Another example is mn is defined as the how do I write it? So the product of the elements in this set p raised to the power l such that n is between p raised to the power l and let us say p raised to the power l plus 1, okay. So for every n, look at the highest prime power that is less than or equal to n, okay, and take a product of all these prime powers. So this also can be shown to be a good modular sequence, okay. But anyway, so this is just a aside. So now what we will show today is the following theorem, that computing iterated product NC1 reduces to the problem of computing a good modulus sequence, okay. So let us see the proof of this. So we want to compute iterated product, so we are given x1 up to xn and we want to compute so we need to compute this term, right, given x1 through xn. So what we will do first is we will use the oracle to get the value of m n square. So we know what n is the number of inputs. So whatever oracle we have for this good modular sequence, we use it to get the value of m of n square. Now one next what we will do is we will factor mn square, okay. Factor mn square into prime powers, let us say p1 to the power l1 so on up to p s to the power l s, okay. And let us say I set C1 as, or I will set Ci as Pi raised to the power Li. For I between 1 and s. So, we just factor all of these, and what we are guaranteed is that all these prime powers are bounded by a polynomial, okay. So, these prime powers are small, so therefore, we can do this factorization easily by a log depth circuit. So, this we have also seen last time that yeah. So, if I have a number which is bounded by a polynomial, then I can factor it in log depth, okay. So, next, so essentially what we are going towards is we will actually use Chinese remandering, okay. So, we will show that we can use Chinese remandering to get the product pi xi, okay. Now, note one thing, so what is product of xi? Okay, okay. So, before getting into that, so let some number. So, we have an oracle, right. So, we are showing we will reduce it to a reduce it to the problem of computing a good modular sequence. So, there is an oracle which given n outputs mn, correct? Huh? Mn is some number, yeah. So, given n it outputs mn.
So, why is it mn square?
So, I give it n square, it will output mn square, okay. So, I give the oracle n square and it will, this is just going to output. So, what do we know about this mn square? Okay, so let us write a small note here. How large is mn square? So, by the definition of good modular sequence, mn is greater than 2 to the power n. So, therefore, mn square is greater than or equal to 2 to the power n square, right. And what can I say about the value of product of xi? How large can a single xi be? 2 to the n, it is an n bit number, so it can be as large as 2 to the power n. There are n of them that I am multiplying, so how large can the product be? So, the product is again at most, actually it is n bits, so it is 2 to the power n minus 1, but whatever. So, it is 2 to the power n square, right. So, this is strictly greater than the product of xi, right. So, basically this term that I am factoring, okay, is bigger than the product, okay. In other words, the product is bounded by this thing, okay. So, now what we will do is we will compute, let us call it B, B of j, which is equal to product of xi, I going from 1 up to n modulo Cj, okay, once again for I between 1 and s. Okay. So, again this is something that we have seen, that if I am computing the product modulo a small number, a polynomial, then we can do this in NC1. This is something that we have seen. So, using that algorithm we compute Bj. Okay. Now, what happens if I use Chinese remandering? Okay. So, recall what the Chinese remaindering problem was. The Chinese remaindering problem was that given n relatively co-prime numbers C1 up to Cn, okay, and given some xi up to xn such that these xi's are smaller than ci's, okay, there exists a unique x, okay. So, this is the Chinese remaindering theorem that I mentioned. There exists a unique x which is less than the product of these ci's, and this x satisfies the property that x mod Cj is equal to xi. Okay. That is what we x mod Ci is equal to xi. That is what we saw last time, and we saw an algorithm which actually allows us to compute this number, okay, given the product. Now, what we will do is that, so in our case, so these Ci's will be the same Ci's of the Chinese remaindering theorem that we had, and the Bi's will be our Xi's, okay. So, use Chinese remaindering theorem to get. So, what does Chinese remaindering output? It outputs this number x, right. So, let me, for the time being, let me just call it as capital X, okay. So, to get x given these C whatever Ci's and Bi's. So, what property does x have? Okay. So, note that what is the product of these Ci's in our case? So, the product of these Ci's is mn square, okay, and mn square is greater than or equal to product of xi, okay. So, what I am alluding towards is that this quantity is actually a solution to the Chinese remaindering problem, product of xi, okay. So, one solution to this problem is the product of xi. Why is that? Okay, so one more condition that we need for Chinese remaindering is that these Bi's are less than or equal to Ci's, which is actually clear because I am taking modulus, okay. So, I can write it over here. I will come to that. So, I will come to that, okay. So, this Bj is less than or equal to Cj by definition. Now, what we have is, of course, that product of xi is less than product of this Ci. So, this is actually I going from 1 to, write it as j, I going from 1 to So, product of xi is greater is less than mn square, okay. So, product of xi and mn square is equal to product of Cj. So, therefore, j going from 1 up to s, therefore, product of xi is less than this product, correct. So, this is one condition that is satisfied. Now, what is the second condition? The second condition is that this number product of xi that we have, I going from 1 to n, mod Cj should be equal to the Bj, okay, for all j between 1 and s. That is also satisfied by the way I computed Bj itself, okay. Therefore, this is a solution. Correct. And by the Chinese remaindering theorem, we know that there exists a unique solution, okay. So, the moment I apply Chinese remainder and I get x, what I have is by the Chinese remaindering theorem, this capital X that the algorithm outputs is exactly equal to product of xi, and we get our answer. Clear? So, what was the idea here? The idea here basically was twofold, actually three things. One is that I am computing a number which is like bigger than the product, and it has the property that every factor, every prime factor, or every power of a prime, or every prime power that divides n square is small, which allows us to factor it efficiently. That is the second thing. And the third thing is the way I design my BJs. Okay, so the way I design my BJs, it becomes exactly equal to what I want finally. Okay, so I define my BJs to be the product modulo CJs. Okay, so therefore the only solution that this input will have is x equal to product of xi. Okay. So what are we left with? So essentially we are left with how do we get this mn square. Okay, so here I assume this as an oracle, given n, how do I get mn square. So and now note that I am not using any particular modulus sequence. This actually works for any good modulus sequence. I have not used a specific fact, and we have seen here some modulus sequences. Okay, so in particular I will take the first one. Okay, so the last part is actually easy. So given n, computing mn square is actually in P. Okay, so we will use polynomial time algorithm over here. In fact, there are actually better algorithms. There are actually ways in which it can be done even in log space, but it's enough. So what we will show, or what actually Cook, Beam, Hoover showed, is that this is a P uniform NC1 reduction. So compute the first n square primes and compute their product. Okay. So quickly let us see why this is a good modulus sequence. So the mn square that we get as a result of this, okay. So what is the product of the first n square primes? Okay. So the product of the first n square primes will be product of, or I mean I do not even need to say this, for I have to show it is a good modulus sequence. So I will just argue for mn. So mn is product of pi, I going from 1 to n, where pi is the ith prime, and what we know by prime number theorem is that pi is at most some C I log I. Okay. So therefore, I mean let us say it is I square, I mean I log I is of course less than I square. So I can write product of pi's as product of I whole square, I going from 1 to n. So this is n factorial whole square, and well, n factorial is of course less than or equal to n to the power n. N to the power n can be written as 2 to the power n log n. So again, so this is basically less than 2 to the power 2 n log n, which is like less than 2 to the power n square. Okay. So, we have by the prime number theorem that Mn is less than 2 to the power n square. So, one condition is satisfied. Of course, each prime is at least 2. Okay. So, therefore, Mn is greater than 2 to the power n. Okay. So, the other condition is also satisfied, and by the prime number theorem, once again the only factors are the primes. Each prime is bounded by n log n. N log n is of course a polynomial, so it is satisfying the next condition also. Okay. So, this is basically showing that the first n primes is computing the first n primes is gives us a good modular sequence. And now essentially what we are doing is we are doing this in polynomial time. So, that is, and that does not matter for us because here, so where are we using? So, here we are using this algorithm to compute Mn square, right, and well, this is actually independent of my xi's, right. So, this is independent of my xi. So, I have to compute a circuit for, so which works for all inputs of length n. So, there I just I actually do not get log space uniformity, what I get is p uniformity, right. So, basically where did I write the reduction? Huh. Hmm?
I mean, how we are getting the oracle that, does that determine, what kind of reduction?
No, the oracle, we do not care how we get the oracle. The oracle.
This P thing you are telling, this is about how we are getting the oracle.
Correct, but now think of the circuit. So, what I am saying is that I actually do not need any circuit to compute Mn square. So, given n, I will just do some pre-computation and I will get the value of Mn square, okay, and that Mn square actually works for all inputs of length n, right. So, I have to kind of show the existence of a circuit, right. So, the answer that we get is, so here I purposefully did not write what kind of uniformity. So, what I get is that division is in P uniform NC1 as a result of this. So, given n, first, so you can think of it like this. So, given these x1 to xn, I do not look at the input, I look at n, I apply a polynomial time algorithm, I get Mn square and then everything else follows in place. Okay. But again, so as I said that there have been works after this which have improved this P uniformity to even log space uniformity, but we will not get into that. So, this completes the